Hello everyone. Today we are going to analyze this propped cantilever beam. In this beam there is a point load 24 kilonewton. It acts at a distance of 5 meter from the fixed end. The total length of the beam is 8 meter. In this beam we have different moment of inertias. For AC the moment of inertia is 2I and for CB it is I. Now we are going to find the degree of static indeterminacy. In this beam, the number of unknown reactions and moments are 3. The available equilibrium equations are 2. The degree of static indeterminacy will be 3 minus 2. It will be 1. Let us take RB as a redundant. To find RB, we are going to use strain energy formula. U is equal to 1 upon 2 EI into integration of m square dx. To use this formula, we have to make sections. In this beam, there are two different parts, BC and CA. So we have to make two sections, one in BC and one in CA. You can see that I have made two sections, one in BC and one in CA. I have made both of the sections at a distance of x from the point B. Since there are two parts BC and CA, we have to split this formula into two parts. This is for BC and this is for CA. For CA, the moment of inertia is 2I. So in the formula, instead of EI, we have to apply 2EI. 2 into 2EI, it will be 4EI. The limit for BC is 0 to 3 and for CA, it is 3 to 8. We are going to find the moments M1 and M2 from the point B. In this case, we have to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. Let us find M1. Up to this section, we have only RB. RB is acting in the anti-clockwise direction so that it will be positive and the distance is x. RB into x, it will be RBx. Let us find M2. Up to this section, we have the point load and RB. RB is acting in the anti-clockwise direction so that it will be positive and the distance is x. RB into x, it will be RBx. This load is acting in the clockwise direction so that it will be negative. For this load, we have to take this distance. This distance is x minus 3. We can multiply minus 24 with this, then we will get this. We know that when we partially differentiate u with respect to RB, it will be 0. In this equation, we can only partially differentiate m1 square and m2 square because these two terms are constants. When we partially differentiate m1 square with respect to RB, we will get this. And when we partially differentiate m2 square with respect to RB, we will get this. We can eliminate this 2 and this 2. We can eliminate this 2 and here it will be true. 1 upon EI is common. We can take it outside and then on the other side 0 into EI, it will be 0. Let us apply the values of M1 and M2. Let us partially differentiate M1 with respect to RB. For RB, it will be 1. 1 into X, it will be X. Let us partially differentiate M2 with respect to RB. For RB, it will be 1. In these two terms, there is no RB, so the differentiation will be 0. 1 into X, it will be X. X into X, it will be X square. We can multiply this with the X so that we will get this. Using this formula, we can do the integration. After doing integration and simplifying, we will get RB, which is 10.575 kilonewton. Now let us apply the rule sigma v is equal to 0 and find RA. Let us take a moment about A and find MA. RB is acting in the anticlockwise direction so that it will be positive and the distance is 8. The point load is acting in the clockwise direction so that it will be negative and the distance is 5. Let us assume that MA is acting in the anticlockwise direction so that it will be positive. For MA, we will get a positive value. That means our assumption is correct. It is acting in the anticlockwise direction. Here you can see the shear force diagram. To find the moment in the point A, we can use right hand side rule. In the point A, we have MA, which is acting in the anticlockwise direction, so that it will be negative. To find the moment in the point C, we can use left hand side rule. RB is acting in the anticlockwise direction, so that it will be positive and the distance is 3. For the bending moment at C, we will get 31.725. We know that the moment in the point B is 0. Here you can see the bending moment diagram. In this point, the moment becomes 0. This is the point of contraflexure. We can make a section in this point and find the distance. You can see that I have made a section in that point at a distance of x from the point A. We know that in this section the moment is 0. Using that concept, we can find x. Now we are going to end this session. Thank you for watching this video.